So this is our section 2.1. We're talking about discrete random variables. So a random variable is we take a variable and we assign numerical values to outcomes of our experiments. So for example, we might want to keep track of the number of radios we sell in a week. So we're going to let x be the number of radios we sell. So if we sell 0 radios, then x is 0. 1 radio, x is 1. 2 radios, x is 2. Makes sense. Before we actually complete the experiment, we don't actually know how many radios will be sold, and that's what makes it the random variable, the fact that we don't know what the value will be until the experiment happens. So before we spend the week selling radios, x, which equals the number of radios sold, is uncertain. So that's the random variable part of it. Now, so it's easy to see, like, if we sell 0 radios, then x equals 0. That seems pretty simple. But we also have times where our outcomes aren't numbers. So I could ask you a question like, if you've taken a statistics class, and the answers you'll give me are true and false. Those aren't numerical. But we can assign our numbers to it, so we could say x equals 0 if you say false, x equals 1 if you say true. Or you could switch it around. Okay, you could even assign it 5 and 6 if you wanted to. And you just, before it starts, you assign a number to each possible outcome. So for our next example, let's consider tossing a coin 3 times and observing whether we get heads or tails. Okay. The sample space is head, 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 tail, head, etc. Can you tell me in advance what you're going to get? Okay. So let x be the number of heads. Can you tell me in advance how many heads you're going to get when you toss the coin? No? So, just to try it, let's see, so that would be a head. Oh, just one head. Tail. And tail. Okay, so what is my value for x here? So we let x be the number of heads. So x is 1. Okay. Am I going to get the same outcome next time I toss it? Okay. Maybe, potentially. What's the probability that I do get the same one next time? Okay. Well, 3 heads in a row, so it's actually going to be 1/8. So this one is tail, tail, and heads. Okay. So different outcome, but what is my variable of x? 1. Okay. And just so I don't have to toss it again, let's say the last one is tail, tail, tail. Okay, so in this case, x is 0. Again, the very important realization that your random variable can change for each time you do the experiment. Then we also have some convention for symbols. Okay. Usually in the lower level classes, they don't even do these, and the books will even do it wrong. But once you get into the mathematically based statistics, we like to use the random variable. We'll use x, y, z, capital letters. But the actual individual values for your random variable, so like up here, when I toss the coin and I got x equals 1, I will write it with lowercase x. So your random variable, before you know what it is, we'll write with an uppercase letter. The actual individual values we will write with a lowercase letter. Not a huge deal, but it helps us keep track of what we're talking about. So next thing we'll talk about is probability distributions. So a probability distribution is we need some way to describe all the possible values of x and the probabilities. Usually we can write this with a formula, a table, or a graph. So let's say we're tossing a fair coin 3 times. Here are all of my sample space outcomes. What should the probability be for each of these outcomes? Okay, they should be equally likely, so the probability is 1/8. And you do actually know enough that you could figure this out now if you needed to. So like if you didn't remember that they're all equally likely. So it is a fair coin, so probability of heads is 0.5, tails is 0.5. So if you want to say the probability of tails, 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 you'd have to do, because we know it's tail and then a tail and then another tail. So we need to multiply. So we do 1/2 times 1/2 times 1/2 gives me 1/8. So let's go through now and label the random variable for each one of these. So x is still the number of heads. Okay, capital X, number of heads, since I don't know what it will be yet. And then, so for the first one, x would be 3 heads. 2, 2, 1, 2, 1, 1, and 0. So if I want to fill in the probability distribution, I say, well, what are my possible values of x? I could get little x equals 0, little x equals 1, little x equals 2, little x equals 3. What is the probability that x equals 0? 1/8, because that's the only outcome that gives me 0. What about the probability that x equals 1? Okay, 3/8, because there's a 1, 1, and 1. So 3/8. For year 2, how many are there? Okay, there's 1, 2, 3 of those as well. So if we add up those probabilities, we get 3/8. And finally, for x equals 3, there's only one of them, so 1/8. So that's how you find a probability distribution. You figure out all the outcomes, and then the probabilities for each value of x. So that was random variables, and then we have what's called discrete random variables. So discrete random variables is a variable x that has a countable number of possible values. So you can count or list all the possible values. It could be countably infinite, okay, but you just have to be able to count it all. So countably infinite is something like where you go 0, 1, 2, 3, 4, all the way up to infinity. Okay, technically that's something you can count. What's something that you cannot count? Okay. So let's put it this way. Can you count the natural numbers? So natural numbers are what numbers? 0. Okay. Can you count? And so 0, 1, 2. So I can count those. It might take a while, but you can count them. Mathematically speaking, you can count them. What about integers? So -1, -2, 1, 0, 1, 2, 3. Okay. You can count all of that. If I went in 0.5 increments, so 1, 1.52, 2.53, 3.5, technically you can count that. When you get to the point that you can't count it?
All reals.
Okay, all reals. Okay. So that brings up something you can't count. But anything that's like integer valued or like 0.5 increments, 0.3 increments, anything like that would be something that you could count. These would be discrete random variables. For discrete random variables, we do what's called a probability mass function, so PMF. And this is the set of probability values, pi, assigned to the xi values for your random variable x for your discrete random variables. So basically, it's make this table for a discrete random variable. Or sometimes we can come up with a formula. Now, your probabilities for your PMF, the rules, is that each probability has to be between 0 and 1. That should not come as a surprise. And if you add up all the probabilities, you should add up to 1. So that's true both for the original outcomes. So looking up above here. Okay. When I added up all of the probabilities of the outcomes, I should get 1. And then even though the probabilities changed when I found the values of x, if I add up these probabilities, I should still get 1. Now we write the probability that the random variable x takes the value xi is the probability pi as such. So we write the capital X to tell us we don't know what it is. So the probability that x equals, say, like 3 would be, say, 0.5 or something. So random variable, specific value, and probability. So for the example we just found, so here, this is the number of heads if you toss the fair coin 3 times. So we have xi, so our specific x values. We have pi, so our probabilities. And is it a valid probability assignment? So we have to check, are each of the probabilities between 0 and 1? They are, and then we have to add up the probabilities. So 1/8 plus 3/8 plus 3/8 plus 1/8. Well, that will give me 8/8 or 1. So we're good there. So this is a valid PMF. Now, Sean thinks that he can model the probability of having x accidents in his factory by this formula. So the probability that x equals your little value, okay, your specific value, is going to be 1 over 2 to the power of x plus 1, where x can be 0, 1, 2, dot, 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 so potentially up to infinity. Okay. And I'm going to ask you, is this a valid probability distribution? So again, let's check it. So is each value going to be between 0 and 1? Do you know for sure they will be bigger than 0? Okay. 1/2 is a positive number, and no matter how many times I raise it up to an exponent, it's still going to be a positive number. Okay. Will it be less than 1? Because, or why?
Because you're dividing 1 by something, so it's always going to be.
Okay. So we have 2 to the power of something, so that's going to be some big number. So we're doing 1 divided by a big number. That gives me something less than 1. The only way it could give me something bigger than 1 is if this became a fraction, which isn't going to happen because it's either 2 to the power of 0, which would be 1, 2 to the power of 1 would be 1/2, well, would be 2 to the power of 2 would be 4. So we're always going to get something smaller than 1. Then you have to check and see if you add up all of these values if you're going to get to 1. So this is a good chance to practice some of your calculus you might not remember. So we want to see if I add it up from 0 to infinity, so it's an x. So x can go from 0 to infinity, that's what they told me there, of 1 over 2 to the x plus 1. I want to know what is that going to give me. So make it easier. So I remind you that we know that if we sum from 0 to infinity of some constant raised to the power of n, we will get 1 over 1 minus r if the absolute value of that number is less than 1. So what do I need to do to this sum to make it look like that formula? Specifically, like, what do I need to do? Okay. So I could write it as 1/2 to the power of x plus 1. But what else do I need to do? That's still not quite like what I have in my formula. What's the difference?
Well, can't you split the bottom so you have the 2x times 2 to the first?
Okay, so this is currently the sum from x equals 0 to infinity of 1/2 times 1/2 to the x. Okay, so I can pull that 1/2 out. Okay, now it looks like my formula is the absolute value of 1/2 less than 1. Yes, so we know that it will converge. So it's going to be 1/2 times, let's see, what will it converge to? It converges to 1 over 1 minus by r, so 1/2. So this gives me 1/2 times 1 over 1/2. 1/2 times 2 gives me 1. Okay, so if I add up all of those probabilities, even though I'm going to infinity, they will add up to 1 eventually. And then I did put in the table and the graph for you. So this was the formula for it. Okay, here's my table. So here are each of the x values and each of their probabilities. And this is the graph. So lots of times we'll do graphs that look like this so you can see your distribution. So at 0 we have a very big probability, and then it gets smaller and smaller very quickly and dies out very quickly. So questions about that problem? So for our next example, let's think of answering a quiz with 3 questions. Okay, so assume that this time, though, a student has studied enough that they have a 0.8 probability of answering any question correctly. Will x be the number of correct answers, be the random variable? Or you could also think of if each one is 1 point, then x could be their score. So here are all of my possible outcomes, which I can find with the tree diagram. So if I want the probability of getting a right, how would you find that probability?
Just multiply 0.8.
0.8 times 0.8 times 0.8. So 0.512. And so the next one for right, wrong would have to be 0.8 times 0.2. Probability for wrong is 0.2. And what is the next one? Okay, so because it's 0.8, 0.2, then 0.8. So 0.128. And then I did the rest for us already just to save us some time. So let's go through, and you can read for me the different values of x. So what would those be? So let's go through and write out our individual x values and the probabilities. So my possible values are 3, 2, 1, and 0. So what is the probability to get 3 correct answers? The only one that gives me 3 is 0.512. What if I want to get 2, though? What do I need to do for that?
Add up all the 2's.
Add up all the 2's, so there's this one, and this one. So that's 0.128 plus 0.128 plus 0.128. .384. And for 1, I need to add up all of the probabilities that have a 1. So that would be here, here, and here. So it looks like they're all 0.032. .096. And finally for 0, the probability of 0 is 0.008. And that is how you find a PMF, or a probability distribution function. Now, what would be the probability in here that I would get 4 correct? 0. What about like 2.5? 0. Okay, so it's usually understood that if it's not on our table, the probability would be 0. Okay. And finally, we might want to graph it. Okay. Whenever you graph anything, you should always make sure you label your axes. So this would be our x values. These would be our probability values. And we just put a line for each one. So when x is 3, we can go up to 0.512. So 0.1, 2, 3, 4, and 5. So for 3, we can go up to 0.512. For 2, we can go up to 0.384. Let's see, 1 is 0.096. And 0 is only to 0.0008. 0.008. Questions on how to do this part? So now we're going to roll 2 6-sided dice and find the sum of the two numbers. Let x be the random variable representing your sum on the 2 dice. So to do this, the easiest way is to draw out this diagram. So dice 2 is on this side, dice 1 is across the top, and then I wrote in all the sums. So what are my possible values of x? X can range from what to what? 2 to 12? Okay. And so for example, how do I find the probability of getting a 2? Okay, so the only way I can get a 2 is if I have a 1 on one dice and a 1 on the other dice, and the probability of getting 1 is 1/6 both times, so 1/6 times 1/6 does give me 1 out of 36. Okay. What about a 3, though?
It's 236.
Because
There's 2 possible options.
okay, there are 2 possible ways to get it. Each possible outcome would have a probability of 1/6. 2 different ways to get it gives me 2 out of 36. Okay. What about the 4? There are 1, 2, 3 ways to get a 4. For the 5s, 1, 2, 3, 4, 4 of them. Okay, so at this point, it's probably easier to just go ahead and write it down yourself. So we get all of our probabilities. Which value is the most likely to come up? The 7. It has the highest probability. Anyone play Settlers of Catan? Why is the 7 the robber? It's the most likely outcome. And then if you've ever noticed, your 6 and 8s are your red numbers, the most desirable, because they should be the next most commonly rolled out values. Okay, so we want to graph it now. So notes across the top I put in our 1 through 12. So these are my x values, and we need to put our probabilities on the vertical axis. And we just draw them in. So I'm going to do a scale of 36, so 1 out of 36, 2 out of 36, this would be 4 out of 36, 6 out of 36. And just draw it in. So 2's, well, how high can a 1 go? 0. 2 can go up to 1. 3 goes to 2. Notice, does it make a nice pattern? How would you describe this? Okay. It is linear. Any other thoughts on ways to describe it? A triangle, is that what you said?
Symmetrical.
Oh, symmetrical. It is symmetrical. And so that's our probability distribution. So let's find some more probabilities. So this is what you'll commonly have to do for your homework and stuff like this. So let's say we want to find the probability that x is greater than or equal to 12. Okay. For x to be greater than or equal to 12, what are my possible values for x that we're considering here? So we want to look at the probability that x equals 10, okay, or x equals what? 11, or x equals 12. X equals 13? That would be the probability of 0, so I don't need to add it in. Okay, so if I need a 10 or an 11 or a 12, what do we do in our probability if we have ors? What should I do with those probabilities? We will add them. So this is going to be the probability that x equals 10 plus the probability that x equals 11 plus the probability that x equals 12. Okay, so you guys have the chart in front of you. What are those probabilities? Let's add them up. So for the 10, that's 3 out of 36, 11 is 2 out of 36, and 12 is 1 out of 36. Which gives me 6 out of 36. Now, if you want, you can simplify this. You'll notice lots of times I don't simplify my fractions, and the biggest reason why is so that I can easily compare them. So if everything adds a denominator of 36, I can compare all of my probabilities very easily. So if I want the probability that x is less than or equal to 3, what probabilities do I need to add up here? Okay, I need the 2. Do I need the 3? X is less than or equal to 3, so I need the 3. Anything else that I need? No, that should do it for me. So 1 out of 36 plus 2 out of 36 gives me 3 out of 36.
Is it less than equal or just less than?
This is less than or equal to. On the x less than or equal to 3?
I don't know, for some reason in my sheet it just says less than.
Oh, okay, so. Yep, the first one is x greater than or equal to 10, then we have x less than or equal to 3. Okay, our next one, though, says x less than 5. Okay, so what x values do I care about here? 4, 3, and 2? So if I add up those probabilities, 1 out of 36, 2 out of 36, 3 out of 36, gives me again 6 out of 36. Okay, what about for x less than or equal to 2 or x greater than or equal to 9? What x values do I want? 2, 9, 10, 11, and 12. Okay, did anyone add that up for us?
36.
11? What about the probability that x is greater than or equal to 3 and x is less than 6? So what probabilities am I interested in here? Or which x values do I need? 3, 4, and 5. So that would be, let's see, correct me if I'm wrong, 2 out of 36, 3 out of 36, and 4 out of 36, right? So 9 out of 36. Okay. What is the probability that x equals 11? Sorry, 13. What is the probability that x equals 13? 0, because it is impossible, and the probability that x equals 1 is 0. Okay. So again, it's usually understood if it's not on the table, the probability is 0. So last chance, questions on discrete random variables. So then we have what we call our cumulative distribution functions. And that symbol or abbreviation is Cdf. So it's a function that describes the random variable x, but now instead of looking at the probability for each x value, we look at the cumulative probabilities. So f of x is defined as the probability that our random variable is less than or equal to that specific value. So like f of 3 would be the probability that x is less than or equal to 3. So if you have your discrete random variable, then you find the CDF by adding up all the probabilities for your, well, so we do x equals k, so for all your k values that are less than or equal to x. Okay. But really, all it means is just add up all your probabilities up to and including that number. Now, the tricky thing is, though, that your cumulative distribution functions, by convention, we define them for all real numbers. So basically, we make a step function, and you find it for all reals. So this is what I mean. So here's the PMF for the number of heads if we toss the fair coin 3 times. Find and graph the CDF. So let's see. So let me start throwing out some x values and tell me what the probabilities would be. So what is the probability for x equals negative 10? 0. Negative 5.5. 0. Negative 3.1. 0. Negative 0.00001. Okay. X equals 0. 1/8. So suddenly it changes at the x equals 0. So what we're going to do is we're going to say, we can do a table, it's probably the easiest. So values of x, and then the cumulative probability. So the f of x. So for all my values of x, for every negative number I tossed out, you told me that the probability was 0. So the cumulative probability is still going to be 0. So for x less than 0, all of my probabilities, so all the cumulative probabilities will all be 0. But as soon as I get to 0, what did my probability become? 1/8. Okay. What would the probability be at, like, say, 0.1? Okay. The probability of x equals 0.1 is 0, so the cumulative probability, if I add them all up, is still 1/8. Okay, and so it's going to keep being, the cumulative probability will keep being 1/8 up until I get to 1. Okay, so we're going to do for 0 less than or equal to x less than 1, our cumulative probability is still going to be 1/8. Okay? Because I haven't added any more probability into it yet. Okay? At 1, it suddenly changes. Okay? Because at 1, how much more probability do I add? 3/8. So if I add that together, I get 4/8. And that stays until we get to 2. And at 2, I suddenly jump to, let's see, so I'm at 4/8 and I need to add in 3/8. So I will be at 7/8. And then my final jump, okay, will put me to 1. Okay, and let's see, I'm running out of room here. What about for x equals 4.1? Still going to be 1. What about for x equals 10? 1, x equals 100. Still going to be 1. So, and for x greater than or equal to 4, f of x equals 1. Since I forgot to write it in. So I guess, could I rewrite this last step? I don't need to stop it at 4. I could just say, for all x greater than or equal to 3, will be at 1. Okay. So every CDF will always start at 0, will always end at 1. Okay. And it will always be increasing. So if you remember back from your calculus when we talked about like non-decreasing functions or increasing functions, things like that, you'll always be increasing because you never have negative probability, so that CDF can never get smaller. Now as far as how we graph it, so these are our x values. We want to graph f of x. So x can be 0, 1, 2, 3, 1/8, 4/8, 5, 6, 7, 8. So until I get to 0, I have a probability of, or f of x is 0. Okay. I'm going to put an open circle on it because 0 is not included there. At 0, I jump up to 1/8. I'm going to fill in my circle, and that goes until I get to, just until I get to 1. Until right before. And then I jump up to 4/8, included, go to 2, not included. At 2, I jump up to 7/8, go over to 3, not included. And at 3, I jump up to 1, included, and I can go on forever. So this is what our CDF looks like. Notice again, it is this step function. And that's the hardest part, is to try and figure out what your signs are over here. Questions about it? So everyone has it in front of you. Go ahead and try example 10 on your own, like without looking up here, and I'll just write it silently, and then after a minute, you can compare your answer with my answer to see if you can figure it out. So does your answer look like my answer? If not, like where did you get messed up? Or why is it different? Anything before we go on? Okay. So on the next page, I have that here's a CDF. Okay. And how could you go back and reconstruct the PMF? Does the CDF look familiar? It's the one that we just barely found, so we can check ourselves to make sure that we have the right answers because we know what the PMF is supposed to be. Okay. So looking at this, so these are our cumulative probabilities. Sometimes they will give you this and they will be interested in knowing the original probabilities for the original PMF. So how do you think you could find this? Okay, so you know what the answers are, so that might help you brainstorm how you could find this. So for example, how would you find the probability that x equals -3? What are your thoughts on how you could find that?
What's the first step? So that is the probability.
Okay, that's where the first step is. So what is the probability? Just go a little more
The
specific.
open circle or that line.
Okay, so you're saying we have the
So the probability is
step right here. Okay. Oh, so you're going to say the probability is 0. So notice that -3. So this is my -3.
mine, it jumps up to 0.1.
It jumped up to 0.1. So what do you think the probability would be? 0.1. Okay, what if I wanted the probability that x equals 0? Well, at 0, notice I also have a jump. Okay, so what do you think the probability for x equals 0 would be?
0.25.
Okay, why?
Difference.
Okay, it's the difference. It's how much you jumped up. So, 0.25. So it's just how much did it jump up? Okay, so for the probability that x equals 2, so that would be this jump right here. Okay, how big was that jump? Let's see, that was, if I can't figure out, it was 0.5 minus 0.35 equals 0.15. So if I want the probability, say, that x equals 5, that would be this jump, and I need to figure out how big that jump is. To figure out how big the jump is, I compare the two numbers. So the 0.7 minus 0.5 gives me 0.2. And for the very last one, probability that x equals 7, it jumps from 0.7 to 0.1. So 0.3. So it's always just how big was the jump at that number, and that will tell you the probability for that number. So it's just reconstructing the PMF, the individual probabilities. Now, of course, your book does have a nice mathematical looking formula. Okay, I would never probably try to memorize the formula. I would just remember, figure out how much it jumped at that point. But this is what I was doing, so f of x just means the higher probability minus the last probability to get your probability at that point. Now we get to do continuous random variables, which luckily for you guys, you're statistics 3000, which means you know calculus, so you actually get to do stuff with continuous random variables. In any other statistics class you would have taken, we would have skipped most of this chapter, okay, because it's all calculus based. So our continuous random variable x can take any values, any and all values in an interval of numbers. Okay? So that means it could be defined from, say, -3 to +7. Any possible fraction or decimal you can think in there is a possible value. Okay? Now the difference between this and discrete is, remember, discrete you could count all of the values, but we know that you can't count all of the values in an interval. Because for any two numbers, you can always find another number in between them, and that will go on forever. So for examples, we have things like, say you have your gas mileage of a randomly selected mid-sized car will be X. Even though we might round our gas mileage usually when we write it down, the actual theoretical possible values for your gas mileage could be like 26, 26.1, 26.005, 26.00034, or something. Okay, theoretically, any of these values is possible, and that's what makes it a continuous random variable. Even though you're not actually going to write down all those decimals, it was theoretically possible. Okay, so your gas mileage could be any number in this interval. That's what makes it continuous. So to actually try this out, we're going to go through, here's a list of variables. We're going to say if they're continuous or discrete and list our possible values of x. So the temperature of a cup of hot chocolate served in a McDonald's restaurant. Okay, because it could be like decimals or fractions or any possible number, right? Okay. What would be your possible values? Okay, theoretically, probably any real number. We don't know. Hopefully, it's probably somewhere between, I don't know. How hot do you want to drink your hot chocolate? Somewhere between maybe 100 and 200 degrees or something. Okay, hopefully it's not negative, but theoretically it could probably be any real number. Okay, what if I have the number of 4 patients taking a new antibiotic, and I want to keep track of the number of patients who experience some distress as a side effect?
Discrete.
It's going to be discrete. And what are my possible x values? X could be 0, 1, 2, 3, or 4. Notice how it can only be 0, 1, 2, 3, or 4. That makes it discrete. I can count the number of possibilities. Okay, the time to charge a battery. Continuous. How long do you think? What are possible values?
Up to a few hours.
Okay, up to a few hours. Theoretically, I shouldn't get any negative time, right? So we'd say theoretically, x could be greater than or equal to 0. Hopefully, probably somewhere in the interval, say like 0 to 10 or something. But theoretically, should be bigger than 0. Hopefully not too big. But it's continuous, so any real numbers in that interval. What about the number of major fires in a large city in the next 2 months? And if I was to write that out, the possible values, could I have 0 fires? 1 fire? 2? Does it stop? Not really. Theoretically, it could go on to infinity. The combined weight of all the desks in this room.
Discrete. It's not, each desk weighs the same. Just
Well, are you sure that each desk weighs the same? Could it be off by like a fraction of an inch?
Gum on the underside.
We might have gum on the underside somewhere. Okay, so So I'm still going to go with continuous. Usually anything that's like weight, height, temperature, anything like that is probably going to be continuous. And again, it should be a positive weight.
Can I ask a question with that?
Mm-hmm.
So, to be discrete, must it be an integer?
It doesn't have to be an integer. I should add one of those on here. The one that I always like to say is, like, when I grade tests, I go in 0.5 increments. Okay? So you either have a 1 or a 1.5 or a 2 or a 2.5. So that's still discrete because I can still name off all of the exact choices for you. But, so even though it's not an integer, it's still discrete.
I was just kind of felt like continuous meant that there was some level of flexibility. Like if our gas mileage would change, were we driving in the mountains all day or whatever, there would be a slight change. But I feel like the weight of the desk is kind of a fixed thing. So I'm kind of, so it doesn't matter whether it's like moving or fixed. It's more if it's in a set.
Yeah, so I kind of think of discrete as like set units, and then continuous is anything that can kind of just be like on a scale. So like my weight, it can change and flex a little bit, but it's still, theoretically, I can be like 0.0035 pounds, can be my units. So it's not like I have to be 0.1 or 0.2 pounds, kind of things like that. That's kind of what I think of. Let me skip down to like 8. So the age of a student in this class. Okay, so what would age be? Okay, so theoretically to me, age is still going to be continuous because you're technically not 26 years old. You're technically 26 years and 1 day and 3 months and 5 hours and 0.2033 milliseconds kind of thing. So I'm still going to think of age as continuous. And we said you have to be at least 18 and less than 100 to be in this class. Okay, so those would be my possible values of x. Theoretically, x can be any number in between those. It doesn't have to be integers, or it doesn't have to be 0.5 increments or anything like that. Okay. And so that's how I always think about it is, unless I know for sure it's discrete, I'm going to go with continuous. So theoretically, if it could be continuous, that's what I'm going to go with. Okay. But I have this next example in here just because it is possible for someone to treat a continuous variable as a discrete random variable. Okay. So like someone could decide to measure the age of a student in this class by categorizing them as less than 20, between 20 and 25, between 25 and 30, or older than 30. So then you're actually in only 4 categories. And if you're only in 4 categories, you can list all the categories, so you would technically be discrete. Okay, and the same thing can happen lots of times when we actually go out and measure things. We're only going to measure you as 20 years or 21 or 22 or 23. And so technically, you could then consider that as a discrete random variable, technically. But theoretically, it is possible to be a continuous variable. And so that's what I'm always going to go with is the theoretically, what could it be? So even though someone might change, I'm going to go with what could it be theoretically. Okay. So let's just finish these off. So 6 would be, the rating on a 1 through 5 scale would be discrete. And the number of specks would be discrete. So now if you have continuous probability distributions, okay, we're going to describe those with curves. Okay? Just because we do have infinitely many possible values of x, we can't draw a line graph, it ends up becoming a curve. Okay? So here are different examples of possible density curves that you could find. Okay? And we're going to think of our probabilities of our events as the areas under a density curve. And in calculus, how do we find areas under a curve? We integrate. So any density curve has a total area of 1 because we know all of our probabilities must add up to 1. Now here's the thing, we can't assign our probabilities to each individual outcome because there are infinitely many possible outcomes. Okay? So I always think about it as if you're trying to put all your possible values of x in a bag and draw one out, if you have infinitely many pieces of paper in the bag, what's the probability of each piece of the paper? 1 over infinity, which would be 0, okay? So our probability of any individual outcome, so like the probability that, say, x equals 8, will be 0. Okay, just because there are so many possible values of x. So you can't find the probability of an individual outcome. Instead, we'll find probabilities for intervals of numbers. So we'll look for a probability that x is greater than or equal to 8, or x is between 3 and 8, etc., things like that. Okay. Now, because the probability of x equals 8 is 0, then we don't care if this is a greater than or equal to, or just a greater than. The probability that x is greater than or equal to 8 is equal to the probability that x equals 8. Okay. Because that probability that x equals 8 is 0. So that makes it really nice when you're dealing with continuous functions. You can get really lazy with your symbols, whether they're greater than or equal to or just greater. So for example, in this density curve, okay, I have my curve describes my probabilities. If I want the probability between A and B, then it's just that shaded area under the curve. The line itself, that blue line, is what we call the PDF, the probability density function. So the probability density function, which we'll write with a little f of x, describes the distribution of a continuous random variable. And the way we define the PDF itself is we say, okay, well, if I integrate the PDF from A to B, that will give me the probability that x is between A and B. And a PDF must meet the following two rules to be a valid distribution. Not surprisingly, it's that all the probabilities must be bigger than 0. So your PDF should be at least 0. And if you integrate from negative infinity to infinity, you should get 1. The area under the curve should be 1. Just a few other notes. Okay, so we sometimes interpret the probability that A is less than or equal to B, less than or equal to B, as the probability of getting an x value between A and B. That makes sense, right? But sometimes we'll also interpret it as the overall proportion of our observations that might fall between A and B. So I could ask you something like, what's the probability that if I select a person on campus, they're between 5 feet and 6 feet tall? Or I might ask you what percentage of people on campus are between 5 feet and 6 feet tall. Both of those, you still find the probability that it's between 5 feet and 6 feet, but you can interpret it two different ways. And one more just proof for the probability of a single point. So we said the probability that x equals a single point is 0. Mathematically, the reason why is if we want to find the probability that x equals a, you would have to integrate from a to a. Now remember in calculus, if you're trying to integrate from a to a, what's that probability going to be? 0. Because we're looking for the area under the curve, what's the width of that area? 0. So the area is 0. Okay. Now we get to actually use it. So we have a certain criminal court judge hears many cases in which the defendant is found guilty of grand theft auto. However, the punishment is not always the same due to mitigating circumstances. Suppose the length in years of the prison sentences has this distribution. So f of x equals 1/9 x squared. And notice this. What does this tell me? Okay. So it's defined from 0 to 3, and what would be the value anywhere else? 0. So basically this means f of x equals 0 for all other x's. So like what's the probability that he sends someone to jail for longer than 3 years?
0.
0. So first let's verify that this is a probability density function, a valid probability density function. So the first thing I need to check is, are all of my values going to be at least 0? So is f of x at least 0? Well, if I plug in any number into an x squared, I'm going to get a positive number. Even if I times by 1/9, that's still going to be a positive number. And the other thing I need to check is I need to integrate it and see if it adds up to 1. So technically, I need to integrate from negative infinity. Let me pick a different color. I need to integrate from negative infinity to infinity f of x dx. So I start integrating from negative infinity to infinity of my, okay. Where is my function defined?
0 to 3.
0 to 3. So I'm trying to say how technical to write out. Technically, I'd have to do the integral from 0 to 3 of 1/9 x squared dx, plus then I'd have to integrate everywhere else, so other x's, of 0 dx. Okay. And what is the integral of 0? No matter what my x values are. It's just going to be 0. So usually this part is 0. Usually I don't even bother writing it down. So even though we say integrate from negative infinity to infinity, we just integrate over the x values that we actually care about. Okay. So if I integrate from 1/9 x squared, what is that going to be? So 1/9 times x cubed over 3, integrate from 0 to 3. So that gives me 1 over 27 times 3 cubed minus 0 gives me 1. And we're good. So this is a valid PDF.
A question. The first, f of x is greater than or equal to 0, does that just have to apply within the range that we're given? Or does it be for any?
Well, it should be for all x values, but if we just write it like this, then we are saying that f of x equals 0 otherwise. And so then it is greater than or equal to 0 everywhere else. Yes, it should be bigger than 0 for every possible x value. So let's graph the PDF and diagram the area that represents the probability that a prison sentence is no longer than 6 months. So what does 1/9 x squared look like as a function? It's a parabola centered at 0. Okay, but do I want that entire parabola? Just between 0 and 3. So between 0 and 3. So it's going to look like this. And everywhere else, it will be 0. Who knew it would delete it? Okay, so it's a parabola from 0 to 3 and 0 everywhere else. Okay. So if I want the area between, so for prison sentences no longer than 6 months. Let's see, this was actually in years. So 6 months would be, what is x? 0.5. So we're looking for the probability that x is what for 0.5? Well, x is less than or equal to 0.5. That's what I'm looking for. So no more than 6 months. So here's my 0.5, and I just need to find that area under the curve. So for my next one, find the probability, or diagram the area that represents the proportion of sentences between 1 and 2 years. So I'm looking for the probability that x is between 1 and 2. Does it matter if I have a less than or equal to? Okay, we said that wouldn't affect our probabilities. So it just said between. It didn't tell you whether or not to include them. It really doesn't matter. I could put a less than or equal to. I could leave it as a less than. It's all going to mean the same thing when we find the probability. So we're just looking for that area under the curve. So now we want to find the probability that a prison sentence is no longer than 6 months. So we're looking for the probability that x is less than or equal to 0.5, since my function gave it to me in terms of years. So I know I'm looking for the area under the curve, so I need to integrate. What am I going to integrate? What are my bounds? 0 to 0.5 of 1/9 x squared dx. Okay. As far as integration, everything that I give you in the test will be just a simple power rule, because some of you may or may not have a calculator that can do integrals. Okay. As far as the homework, you'll probably end up with homework that might give you some more complicated integrals. You're welcome to use your TI-89, remember your calculus, or use a website like Wolfram Alpha to evaluate those. Okay. As far as the test, though, I will give you simple power rules just so that everyone is on the same playing field.
So in the test, we won't be using calculators then?
No, you can use your calculator still, but just in case someone doesn't have an integral capable calculator, I don't want them to be punished. Okay. So let's see what this gives me. So again, 1/9, raise my power by 1, divide by my new coefficient, evaluate from 0 to 0.5. So 1/27 times 0.5 cubed minus 0. .00462. Okay. So the probability that someone's sentence is no longer than 6 months is only 0.004. So they're probably going in longer than 6 months. Notice in 4, I said find the probability that one person's sentence is no longer than 6 months. In 5, I'm asking you for what proportion of sentences is between 1 and 2 years. So what percentage of prisoners go in between 1 and 2 years. So that was where I said we had the slightly different possible interpretations. So what are my bounds for my integration? 0 to 1. Yeah, not 0 to 1. Between 1 and 2. That should give me, what, 7 out of 27? So 0.259. So 25.9% of the prison sentences will be between 1 and 2 years. Question?
Yeah, well, I do have a real-world application question.
Okay.
Is there really such thing as a function like this in judges?
Court?
Yeah.
For that, I have no idea. I have no idea because I have no idea how the courtrooms function. However, if you had enough data on a judge's records, you could make up a function like this. So, I mean, you've all been in math classes probably, or done something where in Excel you say, okay, here's my points. Can you create the line of best fit? So you could find a function that would work, and then you could do all these probability calculations for it. I don't think, though, that they get a handbook that says, like, here's your formula for you.
I did work for a court system, and it's more like a check credit list.
Is it?
Kind of, I assume it works like this, but if you've done it, if you've done the crime before, or if you have done another crime before, that kind of thing.
So they have kind of a checklist to follow. That makes sense. Probably slightly complicated. But you can, find, so if you have any kind of data, you could figure out a good probability distribution that would fit it and do these things for probably any application that you can think of. So for our next example, let's suppose that the sentences given by a second judge have a different distribution. So this one, notice I'm going to change it to a y, just so you are practicing something that has a variable other than an x. So this is f of y equals a times the square root of y, and it's defined between 0 and 4. And then we know that f of x equals 0 otherwise. So that is always implied, that it's just going to be 0 otherwise. Okay. So this is a very common question. It's going to come up over and over in your homework. They're going to say, okay, well, here's an A in there. What does A have to be in order to make this a valid PDF? Okay. So this is what we do. So we start checking. And the first thing that we know we have to check is f of x greater than or equal to 0? Actually, not f of x, f of y. Well, square root of y, is that always going to be positive? Yes, so we don't have to worry about that. But what can you tell me about a, then? A needs to be at least greater than or equal to 0 as well, because otherwise I wouldn't be bigger than 0. So a is a constant, yes, I should say a is a constant. And then the other thing I need to check is that I need to make sure that it integrates to 1. Okay. What are my actual bounds that I need to integrate this on? 0 to 4. Because everywhere else it's 0, so that's not going to affect my integral. So 0 to 4, a square root of y dx has to equal 1. That's what we know. When we're all done, it needs to equal 1. So we need to figure out what my a value is so that it will equal 1. So let's see. So if we actually integrate it, so from 0 to 4, a square root of y, dy, not dx. So what would the integral for that be? We can change my square root of y to, okay, so if we change the square root of y to y to the 1/2, then this is going to be 2/3 a y to the 3/2 evaluated from 0 to 4. So we get 16/3 a. So that's what it actually integrates to, but it was supposed to integrate to 1. So we need 16/3 a to equal 1. So a equals 3/16. Okay. So probably at least half of your homework problems will start off by saying, first you have to find a, and now we'll make you find probabilities and everything else from there. But first you have to find a. So, how are you feeling about this? I actually like our continuous functions because I think it's easier to deal with integrals than it is to try and deal with sums for discrete functions. What? Oh, yeah, sums. Integrals are much easier. Okay, so then just like we did for our discrete random variables, we have our cumulative distribution function again. So this is, again, our CDF. Okay? And again, we define f of x to be the probability that x is less than or equal to that specific value. Okay? The CDF, because we had a continuous random variable, then our CDF will be continuous, and it will be non-decreasing, and it will increase from 0 to 1 over your state space. The book uses the keyword state space to mean your possible x values. So for our last problem, my possible y values were from 0 to 4. So this is how you convert between CDF, PDF, and probabilities. So if you want your PDF to your CDF, so if you want to find your CDF, that's just the probability that x is less than or equal to x. And how do we find the probabilities under the curve? We integrate. So we're going to integrate from negative infinity, or whatever your lower bound is, to x, and then they just have to write f of y dy, so you technically have a different variable. So you can plug in the x. So you just integrate up to your x value. So if you have to integrate to get from your PDF to your CDF, then how would you go back the other direction? You take the derivative. So the f of x is just the derivative of the CDF. And then if you have your CDF and you want to find probabilities, so like the probability that x is between A and B, well, technically the way that you find this is you take the bigger probability and minus the smaller probability. Okay, so the probability that x is less than or equal to B minus the probability that x is less than or equal to A. But the probability that x is less than or equal to B, that's just defined as the CDF at B. Okay, so you just do CDF of B minus the CDF at A. So this is how we do it all. So remember, our sentences given by our second judge have this distribution. So f of y is 3/16 square root of y from 0 to 4. First, we want to find the CDF. So we want to find capital F of y. And we need to integrate. So you go from your lower bound. What is my lower bound here? 0 to y. And then you just put in your PDF. And pick some dummy variable. Like t. So this is the square root of t dt. Mathematically, we have to have a dummy variable if we want to plug in our y as a limit. Lots of times, as I'm doing it, I kind of get lazy and just leave them as y's if I forget. Let's see, when we integrate this, my 3/16 comes out, and then this is 2/3 times t to the 3/2, evaluated from 0 to y. So I think the 3's cancel. That gives me 1/8 times y to the 3/2 minus 0. So f of y equals 1/8 y to the power of 3/2. Okay, and what y values is it defined for? For y between 0 and 4. Okay. So that's how you find the CDF. You just go from your lower bound to your variable y. Use the CDF to find the probability that a present term is no more than 2.5 years. So we're looking for the probability that what? No more than, so y is less than or equal to 2.5? Okay. So I could do a couple things. I could integrate from 0 to 2.5 with my PDF. But instead of integrating, we've already done the integration once. Let's save ourselves some time. Okay. So I could just do f of 2.5 minus, let's see, do I have a lower bound here? It just said less than or equal to 2.5, but what's the lowest it can go? 0. Okay. And we just plug both of these numbers into my CDF. So about 35%.
Can we go 1 minus f of 2.5? Like go something else or?
Okay, so if we do 1 minus 2.5, we do the 1 minus if we want the complement. So what would be the complement of no more than 2.5? That would be at least 2.5. So if I asked you for at least 2.5, then you could have done the 1 minus if you wanted to. So let's try it on this next part. So use the PDF to find the probability that a prison term is at least 2.5 years. So if I wanted to use my PDF, then that means I need to do what to find probabilities? I will have to integrate again. So if I'm looking for the probability that y is at least, so y is greater than or equal to 2.5, I would have to integrate from 2.5 to 4 of my PDF, which was 3/16 squared of y dy. So that should give me, since I've already done it, 1/8 y to the 3/2 evaluated from 2.5 to 4. Let's put that in my calculator. What did you guys get when you plug that in? What did you get? 0.6465. Okay, so that's the probability that y is greater than or equal to 2.5 using my PDF. For step 4, it says use the CDF to find the probability that the prison term is more than 2.5 years. So now I'm looking for the probability that y is greater than 2.5. Okay. So this is where, if I already know that probability that y is less than 2.5, I could just use the complement rule. Okay. How would I do this though if I hadn't realized that I could use the complement rule yet? Okay. Or just any thoughts on how you do this using the CDF?
Use the function and plug in 4. Use the function, plug in 2.5.
So we could do f of 4 minus f of 2.5. So 1/8 times 4 to the 3/2 minus 1/8 times 2.5 to the 3/2. Okay, and it should give you, yes, 0.6465, because notice my calculations here are the exact same calculations that I did here, just to kind of show you that using the CDF or the PDF, it's the same steps, and that's why you get the same answer. Okay, or let's just write ourselves a note that we could have used the complement rule if we thought about it. So the probability that y is greater than 2.5 is 1 minus the probability that y is less than or equal to 2.5. So 1 minus 0.3535. Okay, if you thought about it.
So, like on an exam or in the real world, how do we know whether we use PDF or CDF?
Whichever one you happen to know. So if you only know the CDF, use that. If you know the PDF, use that. Actually, though, I'd say if you know that you're going to find a lot of probabilities, would it be easier to integrate 10 times or to integrate once, find the CDF, and then use the CDF to find your 10 probabilities? Probably be easier to use your CDF than to integrate 10 times. But as far as that, on the test, I might say specifically, otherwise you're welcome to do whatever you want. So, questions to here. Okay. So at this point, so you remember that. I think something